Okay, we're going to go through how to do pretty much all of the questions on the Chapter 8 and Chapter 9 review um, for the practice exam. I have put together a the Chapter 8 and 9 formula sheet with the tables. And so you can see I've uploaded that to Canvas. So you can download that, print it out, do whatever you want with that. And I'd highly encourage you to pay attention to everything that I put on there when you're preparing your note card. And then we're going to go through the practice exam. We're going to look at what formulas you should use for what problems and why you are choosing to use those formulas for those problems. Okay, so first, this right here, number 3, the population mean. Sorry, that's supposed to say the population mean is equal to the mean of all the possible sample means. And the reason why that is because the mean of the sample means is equal to the population mean. If you add up all of the means of all of the sample means, every single sample is represented the exact same number of times. So therefore, if you have a mean of, all of the sample means, it will equal the mean of the population. Okay. Sampling error is the difference between a sample statistic and the corresponding population parameter. And you notice we've got the sampling error right here. And let me see if I can zoom in a little bit. So we've got x bar minus mu equals the sampling error. Then all possible samples of n sizes, this is for number 5, are selected from a population and the mean of each sample is determined. What is the mean of the sample means? Once again, based on the previous question. The mean is the population mean. If you have every single possible sample mean of every single possible sample size of n, the mean of all of those sample means is going to equal the population mean. And once again, when we're doing this, let me see here. I'm gonna paint. Let's try this. We're dealing with several different distributions. Okay. First, we've got. Let's undo that. We've got the first distribution, and we'll call this the population distribution. Okay, then we've got the second distribution. Let's try that again. And then we'll call this the sample distribution, or the distribution of the sample means. Okay, so say we have a population of 3,000. All of the business students in all of Baylor, we've got 3,000 business students, and so we've got a total of 3,000 data points making up this population. But if we make a distribution of the sample means, say for instance, we take 30 at a time, so we take combination 3,000 and 30 at a time, and we would be able to determine the total number of possible combinations or the total possible number of data points that would make up this distribution of the sample means. Frankly, this is going to be a whole lot more data points than the population. And each one of these data points, it's not a single observation, it is the mean of say 30 observations. And so the mean of 30 observations is going to be is going to have less range, if you will. It's going to go from maybe a skewed distribution to a perfectly normal distribution. There's a lot of things that the distribution of the sample means does, but what the distribution of the sample means does for us the most is it allows us to take other samples and compare those samples to the distribution of the sample means. When you have the distribution of the population, you can take individuals or individual observations and compare individual observations to the population. But you can't compare individual samples. You can't compare samples to a population. You can only compare individual observations to a population. And then for the distribution of the sample means, you can compare samples to the distribution of the sample means. So hopefully that clears things up a little bit. Sorry, I lost my mouse here for a second. Where is this? There we go. So, we've got the sampling error is the difference. We're going down to number 6. For a given population with a normal probability distribution, the sample distribution of x bar is a normal probability distribution for. The answer is B, any sample size. Okay, and the reason why it is B is because it's already normally distributed. Okay, you see it's already normally distributed right there. And so when you have a normal distribution and it's already normally distributed, it doesn't matter what you do to it as far as taking samples. You're not going to change the normal distribution. It's already normally distributed. Now, if it's positively or negatively skewed, you're going to want sample sizes greater than 30 in order to make it normally distributed, or getting as close to normally distributed as possible. Okay, or if it has a bimodal distribution, something to that effect, something that's not normal. Okay, according to the central limit theorem, the population mean and the mean of all the sample means are equal. Is that it? Or is the increasing sample size increasing the sample size decreases the dispersion of the sampling distribution? The sampling distribution of the sample means is approximately normally distributed, and the sampling distribution of all sample means will be skewed. So which one is the correct answer? In order to know the correct answer, we really have to know the central limit theorem. Okay, so if all samples of a particular size are selected from a population, the sampling distribution of the sample means is approximately normally distributed. Okay, so the answer right here is C. Okay, some of these might be correct, but what we're asking for is according to the central limit theorem. If there's one definition I really want that you really need to know inside and out, it should be the central limit theorem, because there's a lot that's based on that. Also, according to the central limit theorem, what is true of the following? Sample size is important when the population is not normally distributed. And this is the correct answer right here. Although other answers might be correct as well, A is the most correct answer, because the approximation improves with larger sample size. That's what this is saying. Sample size is important when the population is not normally distributed. Okay, so the correct answer there is A. So let's go on to number 9. An experiment involving selecting a random sample of 256 middle managers for a study. One item of interest is their annual income. Okay, first of all, you've got a random sample of 256. Let me... hold on. There we go. So you've got a random sample of 256 middle managers for a study. One item of interest is their annual income. So the number is 256. One item of interest is their annual income. The sample mean computed as 35,420 with a population standard deviation of 2050. So let's look at this sampling. What is the standard error? We found the standard error of the mean. This right here, this symbol means standard error of the mean. And so we've got the standard deviation over the square root of n. So 256, the square root of 256 and 2050 divided by the square root of 256. So 2050 divided by the square root of 256. And so we calculate, let's pull up the calculator. (256) square root is 16. So we've got 2050 divided by 16. Divided by 16 equals 128.125. So the correct answer is A. Okay. So you're using, when it asks for the standard error, use the standard error of the mean formula. Okay. Bones Brothers and Associates prepare individual tax returns over prior years. Bones Brothers has maintained careful records regarding the time to prepare a return. The mean time to prepare a return is 90 minutes. Okay, so we've got the mean time of 90 minutes. The population standard deviation for the distribution is 14 minutes. Notice there, really important is the population standard deviation. When we have a population standard deviation, we use z-scores. If we have only the sample standard deviation, we use t-scores. Okay, so suppose 100 returns from last year were selected and analyzed. What is the standard error of the mean? Okay, well, we're going to look for the standard error of the mean again. And so this time we're not really even dealing with z-scores, but I just wanted to make that note. So we've got the standard deviation. So where is the standard deviation? Standard deviation is 14. And then we have divided by the square root of the number. So of 100. And so you've got 14 divided by 10, which equals C, 1.4 minutes. Okay. Next, suppose a research firm conducted a survey to determine the mean amount steady smokers spent on cigarettes during a week. A sample of 100 steady smokers revealed the sample mean is 20. So right here we've got a sample mean of 20. The population standard deviation is 5. What is, now notice the population standard deviation. So when we were talking about those two distributions, this is the population distribution, the population standard deviation, not the distribution of the sampling means. Okay, when we talk about the distribution of the sampling means, the standard deviation in the standard deviation in the distribution of the sampling means is referred to as the standard error of the mean. Okay, so right here, when we are calculating the standard error of the mean, what we're really saying is what is the standard deviation of the sampling distribution of the mean. Also, same thing right here. When we calculate the standard error of the mean, we are saying what is the standard distribution of the sampling distribution of the mean. Okay, so suppose a research firm conducts a survey. So we've got all of this information. What is the probability? So we're looking for probability that a sample of 100 steady smokers will smoke between 19 and 21. Or will spend between $19 and $21. So we've got the mean, and so we're going to use this fun formula, x bar minus mu over, what should we use? X bar minus mu over the standard the standard deviation divided by the square root of n. But you're looking at this and you're like, we have x bar, right? The sample the sample mean is 20. So shouldn't we put x bar right there? And the answer is no. And the reason why is we're using something called a point estimate. Okay, and so let's take a look at what a point estimate is. A point estimate is the statistic computed from a sample information that estimates a population parameter. So we're going to use x bar right here as the standard or as the population mean. So we've got 20 for the population mean, and we're going to do 19 minus 20 over the standard deviation of 5 with a square root of the number observed, let's see, 100. Okay, so, and it's 5 divided by 100. And so 19 minus 20 is 1 over 5 divided by 100, the square root of 100, or 5 divided by 10. 5 divided by 10 is 1/2. No, yeah. Okay, so 0.5. So 1 divided by 0.5 equals 2. Okay, so that is the z-score, okay, because this gives you the z-score. The z-score for 19 with a mean of 20. Okay, so if you want to know what is the probability based on this sample, what is the probability of an individual spending between $19 and $21? Well, we just calculated the z-score based on this sample of an individual spending $19. So that's the z-score. So let's take a look at z-scores for a minute. We've got two different z-charts. Okay, this z-chart right here, if you've got a z-score, so we've got a z-score of 2 right here. So we find 2, and this right here is the probability of an individual or the probability of the sample being above 2 standard deviations above the mean. Okay, but that's not exactly what we're asking for. Okay, so if we're asking what is the probability of an individual being at 2 standard deviations above the mean or higher, or 2 standard deviations below the mean or below, this chart will give that to us. Okay, but if we are asking what is the probability of an individual being between the mean and 2 standard deviations above the mean, okay, so let's take a look at this. 2.4772. So we've got 0.4772 right there. So that's the probability of an individual, or in this case, the mean of a group being between the mean of what is the probability that a sample of 100 steady smokers spends between $19 and $21? This is the probability that the sample will spend between 100 or between 20 and 19. Sorry, I messed up. 19 minus this is -1. So that gives us -2. Okay, so it's a z-score of -2, and so we find 2, 4.772, and if you figure out on the other side, sorry about the negative, but if you look at doing it the exact opposite with 21 minus 20, oops, it goes a little off the edge there, 21 minus 20 over 5 divided by the square root of 100, that will give you the z-score of 2. So you've got the z-score of 2, and then you've got the z-score of -2. And so if you come over here, you've got the z-score of -2 right here, and the z-score of 2 over here. And so what you're trying to find is what is the probability of an individual being between all of this, right? And so you can use the area under the normal curve for this. This number down here, this 2 right here, tells you the probability of an individual being from the mean to 2 standard deviations above. Okay, so you get 4.4772. So when you're looking at what's the probability of a sample being between 2 numbers, if the 2 numbers are around the mean, it's really easy to use the area under the normal curve z table. Okay, because you've got the 2 over here, and so you can find the probability of being from 2 to the mean, and then add it from the probability of being, or from -2 to the mean, add it to the probability of being from 2 to the mean. So you've got 4.772 and then you also have 4.772 on the other side. You multiply that by 2, and it gives you C. Okay, I'm going to break up this lecture, and then we're going to continue with number 12 in the next lecture.